Hey everyone, Mr. Shafter here to continue the conversation of definite integrals, and in this video start to relate them to antiderivatives. Objectives: to examine rules for integration, to define average value or mean value, and to relate the mean value theorem for definite integrals as it was related to derivatives. This should be capitalized, that bothers me. Let's jump in. Number one, a couple of quick rules. Order of integration: if you integrate from b to a of f of x dx and you switch that from a to b, so your bounds switch, you have to factor a negative out of the integral. All right, that's just the definition. Number two, if you integrate from one number to that exact same number, the answer is always 0. No area has accumulated from one number to that same number. Number three, super useful, constant multiple. If you have a constant inside of an integral, it can be pulled out of your integral. You can then integrate happily and multiply by your constant at the end. If it's a negative, obviously, the constant is just -1, but the same thing applies. Number four, just like in derivative world, you can add and minus, add and minus, escaped me the word, minus, subtract, add and subtract integrals. Whether you integrate first or add and subtract first and then integrate second. So basically what it says is if you're integrating the two functions f of x plus g of x or f of x minus g of x, it's the same thing as integrating f first and then adding or subtracting the integral of g. So you can do it in either order. A couple more important ones. Additivity: if you integrate from a to b of f of x dx and you add the integral from b to c of f of x dx, it's really just integrating from a to c. Notice we ended the first one at b and we picked up the second one at b, so we haven't changed the value. Number six, max-min inequality. If you know the minimum and maximum value of f, then the integral itself from a to b of f of x dx will never be any smaller than the minimum value of f times b minus a, and it will never be any larger than the maximum value of f times b minus a. The minimum value of f or the maximum value of f multiplied by the difference of your bounds is just the integral of the constant. So these values right here are just assuming that the function takes on its minimum value for all of the region a to b or the maximum value for all the region of a to b. Last one, domination. If f is always greater than or equal to g on a to b, then the integral of f from a to b will always be greater than or equal to the integral of g from a to b. This makes sense, right? If f is always bigger, then it will always have more area between the curve and the x-axis. One last thought: if f of x is greater than or equal to 0 on a to b, then the integral of a to b f of x dx is greater than or equal to 0, not considering g at the moment. Let's try some examples. A, the integral from 4 to 1 of f of x dx. We're going to use a swap bounds here. We're going to integrate from 1 to 4 of f of x dx. But when you swap your bounds, you have to pull a negative out of your integral. Well, I do know the integral from 1 to 4 of f of x dx is -2, so the answer is simply negative that I pulled out. -2 is equal to +4. B, the integral from -1 to 4 of f of x dx. Well, I don't know that. But what I do know is that the integral from -1 to 1 of f of x dx, and I can add the integral from 1 to 4 of f of x dx. And this is additivity. These integrals together added up are just the integral from -1 to 1, -1 to 4 of f of x dx. So the integral from -1 to 1 of f of x dx is simply given to me as 5. And the integral from 1 to 4 of f of x dx is -2, so the answer is just simply 3. So the integral from -1 to 4 of f of x dx is 3. C, this one's a little long. We've got the integral from -1 to 1 of 2 times f of x plus 3 times h of x. Well, the first thing I'm going to do is use a sum and difference rule. I'm going to split these up. So let's do integral -1 to 1 of 2 times f of x dx, and then plus the same integral, -1 to 1, of 3h of x dx. Then I'm going to use constant multiple and pull my constants out of my integrals. So I've got this one plus 3 times this one, and I know the values. -1 to 1 of f is 5, and h is 7. So this is 2 times 5 plus 3 times 7, which is 10 plus 21, which is 31. So the integral in C is equal to 31. D asks for the integral of 0 to 1 of f of x. Integral 0 to 1 of f of x. Well, I don't really have that. I've got negative 1 to 1 and 1 to 4, and I can't really use those to create 0 to 1. And one of the answers here was that it's not possible. So that's the answer here, D. You can't figure this out. Not possible. No information. Example 2. Show that the value of the integral from 0 to 1 of the square root of 1 plus cosine x dx is less than 3/2. Whenever you're trying to show that an integral is greater or less than a certain number, you're using the max-min rule. So I'm just going to use the right side inequality because I'm trying to prove it's less than something. So the integral from, you know what, I'll just write the theorem, from a to b of f of x dx is less than or equal to the max value of f times the difference of your bounds. So once I find the maximum of this curve on the interval 0 to 1, I just multiply it by 0 minus 1, or 1 minus 0 rather. So this shouldn't be too bad. So if the original curve is the square root of 1 plus cosine x, and I want to find the maximum value, I simply find the derivative. So the derivative is equal to, this is just 1 plus cosine x to the 1/2. So the derivative is equal to 1/2, let's just do square root of cosine x and times negative sine x. For a derivative of the inside, you have to chain that. So this is the derivative. I know the derivative is going to equal 0 at x equals 0. And I know the derivative will be will not exist. So I'll just write does not exist at x equals pi, because the denominator would be 0. But since I'm working from 0 to 1, I actually can just exclude this altogether. So I know that x is going to be 0. So if I plug 0 into my original, I want the y value. 1 plus cosine of 0. This is going to be the square root of 1 plus 1, which is the square root of 2. And I know that to approximately be 1.414. Well, I'm trying to prove the integral is less than 3/2. But I know the maximum of the integral from 0 to 1 of we'll just put the curve in there, 1 plus cosine x dx, is the maximum value, which is the square root of 2, times b minus a, which is equal to the square root of 2. So since the square root of 2 is 1.414, which is less than 3/2, which is 1.5, the integral from 0 to 1 of the square root of 1 plus cosine x dx must be less than 3/2. And that's evident because we know that the highest it could possibly be is 1.414. Look at that, I didn't even need my extra page I gave myself. Sweet. New definition time. Average value, otherwise known as mean value. The definition says, if f is integrable on a to b, closed interval, its mean or average value is the following. So it's the 1 over b minus a, which is 1 over the difference of your bounds, multiplied by the integral a to b f of x dx. And what you're solving for here is a y value. Average value is a y value. So what exactly is average value? We know the average value of a list of numbers is just simply the sum of numbers divided by the quantity of them, right? But how could you possibly find the average value of a function? It has an infinite number of values potentially. So let's talk a little bit about what this actually is. And to do that, it's best to show you a picture. So the average value of this function is basically going to be some y value. So it's going to be some y value, okay? Such that if you were to draw a rectangle right here at this y value, all right, so whatever this magic number is, you draw a rectangle, and you find the area of this rectangle by just simply doing base times height, which is the base is b minus a, and the height is f of c, and you multiply them together, and you find the area of this rectangle. It's actually going to exactly equal the area under the curve, which is the integral, which I'll just kind of highlight right here. So this magic number, whatever this value is going to be the exact moment that the area of this rectangle, when drawn, will exactly equal the integral, the area under the curve. The mean value theorem guarantees the existence of this value. So the mean value theorem basically states that f of c has to exist as long as f is continuous on a to b. C is the x value that produces the mean value. So if I go back to my picture for a minute, C is just this number. It's quite useless. I shouldn't say useless, but it's not really that important. It's really just some number between a and b, just like the mean value theorem for derivatives, okay? What we really care about, though, is the f of c, the function value at c, the y value, when you plug c into f of x. That's the cool value. That's what makes the rectangle's area identical to the integral. The mean value theorem assures that it will exist. Number 3, find the average value of the function without integrating. So let's use geometry. So you have a nice triangle here. Remind ourselves of the average value. So the average value is equal to 1 over b minus a times the integral from a to b of f of x dx. Obviously 1 over b minus a is quite easy. The interval is -4 to 2. So it would be 1 over 2 minus 4, which is just 1 over 2 plus 4, which is 1/6. And then the integral is the area of the triangle. It looks like this would be pretty easy to figure out. Looks like it has a height of 3, and it has a base of 6. 6 times 3 is 18. So the area of the triangle will simply be 1/2 base times height. It'll be 1/2 times 6 times 3, which is half of 18 is 9. So the answer to the average value is 1/6 of 9, which is 3/2. Looks like we can't escape that number. 3/2 is the magic number.